across the proximal convoluted tubule, where we did that reabsorption and secretion, past the nephron loop, where we created our gradient, but we end up with a dilute filtrate in our distal tubule. And remember, this is anatomically incorrect. This should actually be way over here. Okay, you guys remember that? And then it goes into the collecting duct. Now, this being a juxtamedullary nephron, that's why the nephron loop is actually working to separate components. We're going to have our cortex and our medulla. The distal convoluted tubule, like the proximal convoluted tubule, is always present and only present in the cortex. Okay, so again, capsule, proximal, distal convoluted tubule, we only see in the cortex. Nephron loop, if it's a short nephron, could be in the cortex. If it's a juxtamedullary nephron, it would be in the medulla. Right? So as our filtrate is moving up into the collecting duct, it's going to be dilute, depending on whether or not we add aquaporins. So the distal tubule and the collecting duct are where we see hormonally regulated reabsorption or secretion and fluid and electrolyte control. There's several pages in your lecture notes and a whole chapter on electrolyte and fluid balance that I'm not going to lecture on. You know, the effects of hypernatremia and hyponatremia. Those are in your lecture notes, and tomorrow we're going to do acid-base balance. So this is the limit of what I'm actually talking about, the balance of those electrolytes. Most of you know that sodium is higher outside the cell, and potassium is higher inside the cell. All right. We talked about high altitude cerebral edema, and so if you have hyponatremia or hypernatremia, you start changing the amount of extracellular or intracellular fluid. With the increase in running over the last 30 years and exercise and all of that, marathon runners, long distance runners, you have all the water stations, and people are constantly, drink. You need water before you actually feel thirsty. A few people every year die from drinking too much water while they're out exercising. Even the Gatorade components even though they have more particles in them than water does, it's still hypoosmotic to your blood. So if you drink 5 gallons of Gatorade, you can still dilute out the content of your body fluids. And so currently now, standard at most of our marathon cities, including here in Sacramento, is, in response to this, is that if someone collapses on the run, they don't immediately start an IV. They can wait until they get to the emergency room and do a blood test and see whether they're hyper or hypo. If they're hyper, you'll start giving them IVs. If they're a hypo, that's the worst thing to do. And there's enough time to wait on that. Okay? So we're going to look at several different ions which are regulated at the distal end and to some degree in the collecting duct. First one is sodium. Remember, most of our sodium was reabsorbed across the proximal convoluted tubule, about 65 to 80% of that. About another, well, actually about 65%, another 20% or so in the nephron loop. And the rest of that we adjust depending on the body's need for fluid volume and blood pressure. Along with sodium, 2 other ions end up being regulated indirectly. So if we move sodium, if sodium is in our filtrate, and we move sodium back to the blood, what is going to come with it? Ions. Chloride, to maintain the neutrality of the charges. So that's going to come with it passively. What's going to go in the opposite direction? We have pumps for that. Hold on just a sec. So in the opposite direction, because of our sodium-potassium pump, we have potassium going out. So if this is reabsorption, this is secretion. All right, and this is happening in our proximal convoluted tubule. It's just that in our distal convoluted tubule, this movement is regulated by the hormone aldosterone. Now, as we will see tomorrow, I can't write and look away from the board at the same time. As you'll see tomorrow, we also talk about the acid-base balance, which we have an antiport, and we exchange sodium for hydrogen ions. We also will exchange chloride, and this is, you go either direction, for bicarbonate ions. Okay? So we'll look at the hydrogen chloride bicarbonate component tomorrow. But I want to focus for now on aldosterone. Aldosterone has cells that...
Is there an abbreviation for aldosterone?
No. Have cells that are present, have receptors that are present in cells of the distal convoluted tubule, and also present in cells of the collecting duct. These cells that have receptors, and I'm running out of board space here. These cells that have receptors, microvilli are scant, are going to be present on the basal lateral end because aldosterone is a hormone. Hence, it's going to be coming from the blood. So the aldosterone is going to come in from the bottom of the cell. How about we call it aldo? Receptors are inside the cell. Why do we know that aldosterone receptors are present inside the cell? It's a steroid. All right, so it's lipid soluble. Anybody remember what organ produces it?
Kidney.
Close to the kidney. Adrenal glands. Okay. So when is it produced? This is regulated, remember? So hormones, additional sodium will not be taken up from the blood unless aldosterone is present. So this is a systemic regulation of blood pressure. Remember we talked about autoregulation? And autoregulation, if flow through the afferent arteriole was low, the macula densa would release molecules, adenosine actually, prostaglandins rather, that would cause the vessels to change diameter. We'd have an increased flow rate. So that's autoregulation right there at the kidney tubule. But let's say that you're dehydrated, you're hemorrhaging, you've got ulcers in your stomach and you're losing blood. That's a systemic effect. That's going to result in decreased pressure here in the afferent arteriole. And so as a response to that, those granular cells or juxtaglomerular cells will release, get to my picture here, thought I had it here, will release renin. So that is what the granules are. So we have this process, and I'll redraw this stuff on the board. I just need board space. So due to low pressure, decreased hydrostatic pressure in the afferent arteriole.
Is it just the low pressure or is it also sodium?
This isn't sodium, this is hydrostatic pressure. We covered this briefly when we did blood pressure control. All right, this is a systemic regulation due to decreased hydrostatic pressure in the afferent arterioles, the next thing that happens is the granular cells, the juxtaglomerular cells, release, can't even spell, release renin. This is not the renin that's gotten from calf stomachs and is used to make, what is it called, junket? They use it for cottage cheese and stuff to curdle milk. All right, this is a different kind of thing. This is an enzyme, it is not a hormone. Okay. Renin works on the conversion of a protein. This is kind of like fibrinogen going to fibrin. So it works on a protein known as angio, which refers to blood, tensinogen. It increases the rate at which that is converted to a molecule known as angiotensin 1. Now, angiotensin 1 is itself a vasoconstrictor. It causes smooth muscle to constrict. So throughout the body, it's going to elevate blood pressure. Okay? But it's not the most potent or strong form. Angiotensin 1 travels in the blood to the lungs. And in the lungs, another enzyme known as angiotensin converting enzyme, or ACE, converts angiotensin 1 to angiotensin 2. This whole pathway is what I left out when we were doing the heart.
Isn't there some ACE in the kidneys too?
Not enough to activate everything. Its primary location is in the lungs. Angiotensin 2 is also a vasoconstrictor, a very strong vasoconstrictor. But it has another effect. This is the last one I'm going to write up. And angiotensin 2 stimulates the adrenal glands to release aldosterone. So aldosterone then goes to our distal collecting ducts and our distal convoluted tubules and our collecting ducts. And its effect is on the DNA. It causes transcription to occur, and more sodium potassium pumps are synthesized and inserted into the membrane, and more leaky channels are inserted into the membrane, and we reabsorb more sodium. With more sodium, water follows. All right, so we have, you have to have some ADH because we have to have some water channels for that. So water follows.